Welcome everyone to this week's CVAS lecture given by Valerio Lucarini. A few words about Valerio. He actually studied physics, climate physics and chemistry in Italy, in Pisa and in Cambridge in the US.
Yeah.
And he holds a PhD in physics from the University of Joensuu.
Yes.
Yeah, in Finland, which apparently has renamed itself, but in Finland. So that's actually an interesting thing that I will ask you at some point in the future, how you ended up from Italy and Finland. I'm imagining whether, like these days, imagining going from Italy to Finland, that might be also a large change in temperature.
Well, yeah.
And so since 2011, he was a professor of theoretical metrology at the University of Hamburg. And in 2017, you moved to the University of Reading to also head the Center for Mathematics of Planet Earth. So you've always been a very strong European, I imagine, from your background, and also with a very broad perspective and theoretically founded perspective on climate change and metrology. And so therefore, I'm really looking forward to your talk on heat waves and cold spells, and so bridging the scales, the time scales between climate change and metrology and weather, so the snow events that we are currently seeing, even in London. I'm looking forward to your talk.
Thanks a lot, Kira, and thanks a lot everyone for being here. Yes, I've been moving around a bit, and about Finland, it's a bit of a magic country. Came in a very difficult moment of my life, and it was fun. I mean, I will always be so fond of that country and so grateful for the opportunities. I was one of those who enjoyed the magic of the peak of, when Nokia was the largest company in the world, and Nokia was 1/10 of Finnish GDP. So I tell you the procedure at the time to get a PhD scholarship, if you were in anything that was vaguely related to condensate matter physics, if you were a professor at the university in Finland. My then supervisor sent an email to one email address of Nokia, basically, asking, I have a good student. He might do good PhD on this. And the answer was, okay, you have a grant. That was, because Nokia was a socially oriented company, so they would distribute things to the community. So it's actually a very serious and very important thing. So the opposite of Apple, or, so that's very important. And I appreciated that a lot. So I'm here also for that. So today we will talk about something which sits between, let's say, climate science, physics, and math, which is more or less the area where I like to spend my time, my mental time, at least. So we have now, so Kira mentioned the Center for the Mathematics of Planet Earth. So this is a structure which is now officially incorporated in the University of Reading as one of its 10 interdisciplinary research centers, which means a little money, but a great honor. So we exist officially, and we are, of course, there is a lot, increasing number of people who are affiliated. We have quite large, broad range of research lines, from climate risk, even in a very applied sense, to statistical mechanics and functional analysis, with relevance and stochastic processes with relevance for climate. Please visit the website and please check out what we're doing. And if you want collaborations, here we are, or exchange of staff and students, we are there for that. Okay, so extremes. We're going to talk about extremes and why it's important to study extremes. So there are different reasons why you want to study extremes: because you like headlines, because you have some fetish for disasters, and you are interested in human and environmental welfare, or you're interested in basic sciences. These are all good reasons to study extremes. And of course, extreme events, they're rare, but they have a disproportionate impact in terms of social and environmental hazard, because systems, by definition, can absorb fluctuations near their average, but when the fluctuations are too large, the damages go up very, very rapidly, okay? So that's a general idea about any sort of organized or self-organized system. Now, when we talk about extreme, there are, we use this word in many different ways. So there is a sort of common language use of the word, and there are technical usages of the word. So when we talk about extreme, we might mean something that's very rare. It might mean something that's large, or something that has a large impact, okay? And sometimes these concepts come together. Sometimes they are different. And anyway, if we use this word in a scientific work, we have to try to use it in a technical sense, not just in an evocative sense. Of the risk is that we are talking about an ill-defined object. And this has very substantial consequences on what we do. Also, when we talk about an event, we should specify the spatial and temporal scale of interest. And I will touch all of this. Now, let's go a bit to the language of hazard, natural hazards. So the common way extreme events, high impact events in this case, would be classified is through the slow or fast onset category. So when you talk about slow onset events, you're talking about drought or cold spells or heat waves. So these are events that have long time scale in a physical language. And when you talk about fast onset, you're talking about flash floods as an example, or tropical cyclones. These are fast. They have a small time scale. Of course, you should ask yourself, small or large with respect to what? Okay. Now, common sense approach. We choose a climatic variable. We define something that we assume it's normal, and then we say it's extreme everything that's outside this. By the way, there are many books on the history of science and in fact philosophy of science that that somehow discuss this in general terms. And by the way, this is the way medical statistics is done. Okay, that's when, and so that's how it's defined that you're fat, like me. Okay, or you're tall or you're small. Okay, so when I was a child, people told me that I'm small, and I answered, yes, I'm small. Instead, you're tall. Okay, good. So what? So the problem is that what's wrong or bad or with it, this is a very general concept of society. So we see that there are issues here if we use this approach, because we have to make assumptions on the underlying distribution. We have to define a threshold. Okay, compared to LeBron James, most people are very small. Okay. Compared to Messi or me, most people are very tall. Okay, and the duration. Why? How do you define these statistics? Okay, standard way, through which, by standard mean IPCC standard way, to look at extremes in a changing climate. So you look at the first 2 moments of the distribution or whatever. So this is a sort of really the way more typically things are looked at. So as an example, so we have a changing temperature with a changing distribution. So the mean shifts, the variability shifts, and depending on what we look at and the relative change of mean and variability, you might have a change in the hot or cold extremes. So all of this is under the assumption that what matters are the first 2 moments of the distribution. This is a very, very, very big assumption. By the way, precipitation works in an entirely different way, just to talk about a slight, totally irrelevant climatic quantity. But we will see that this picture, this so nice and comforting, comes back if we look at the problem in a different way. Clearly, this is insufficient. So the state of the art, like almost every time we talk about real applications, is vastly insufficient. So we need research to address applied problems. Now, an important problem, which is the narrative of climate change. Until recently, people would talk about climate change, but I found there was in 2018 an amazing article by The Guardian. I mean, you don't often praise news outlets these days, where they explain why they're not going to use anymore the expression climate change, but you're going to talk about climate crisis. And that they do that, and I'm using it, and because it's a very technical term, in fact. So if you talk about climate change, you have in mind the slow increase of temperature, but this is not the most important thing. So the change in the climate is not the change in the averages, it's the change in all moments of the distribution, and in particular, it's about the changes in the extremes. So this is, I encourage everyone to use this. expression. And this is entering now, as subtle as it seems, you know, it's entering what you find as an example in the sort of, I mean, this slide is, I took some pictures from the Met Office, UK Met Office popularization pages. They were trying to give you a sense of what is climate change. Instead of telling you temperature goes up by 2 degrees, who cares? Because this is the issue. Nobody perceives. If you ask someone, is it good that temperature goes up 2 degrees in summer and you live in Britain? The answer would be great. Okay. But this is not the issue. So now they're using this. Okay, they say that in the UK, the risk of heatwaves, which are annoying because people sweat, increases by a factor of, there is a risk of increasing by a factor of n, where n is large. So people understand that the problem has to do with changes in the higher moments of the distribution. So this is actually very powerful, okay? So now, if you want to have some idea, maybe, I wrote recently with Michael Gill a long review papers, Reviews of Modern Physics, where we tried exactly to bridge the gap between statistical physics and climate science. And we try to discuss this problem in detail. So I'm not going to talk about this. So the relation, climate change as climate crisis and the relationship between climate variability and climate change. This is the topic of this review paper. Today, I'm going to focus on extremes. But still, I will try to make clear that the importance of of defining a good mathematical framework to get results that you can apply. So it's not just a rigor for rigor's sake. I mean, and you're never rigorous enough. In fact, but it's because you want to have some well-grounded concept. So when you look at about extremes, I mean, in some sense, the way to look at extremes in many cases is through extreme value theory. So the nice thing is you have some universal family of distribution that describe extremes if you construct extremes in a well-defined way. So either by looking at peaks over threshold, with threshold that becomes very large, or if you look at block maxima, where the size of the block becomes longer and longer. So these are two approaches that have a long history, and they're, you know, a sort of a beacon of probability theory. And something you can prove, and this is something we did also in this book on the left, is that you can use this methodology to study the outputs of a chaotic dynamical system. And by looking at extreme, you learn about the properties of the underlying dynamics. So this is the other concept, that looking at extremes not only is cool, not only is important, but allows us to learn a lot of things about the underlying system. And we will see this today. No, but I will not here use extreme value theory, which I mean, really, I got sick of it. And I didn't work on it after writing on the book because I couldn't take it anymore. I tried correct the 3,000 typos in the proofs of a 300 pages book, and then believe me, you don't want to see that anymore. So, but what is the problem? I mean, extreme value theory gives an enormous. Allows us to really learn a lot about the climate system. There is a problem, is that extreme value theory, by its very structure, does not like to deal with persistence. Okay, so you can indirectly address the problem of persistence, but it is a sort of a side, a way to go around the problem. Instead, if I want to look at persistence as part of the story, extreme value theory is not really the best approach. Still, so the nice thing about extreme value theory is that regardless of whether you look at the problem from the point of view of block maxima or peaks over threshold, you get asymptotically the same knowledge of the system, even if the candidates for extremes are different. So this is the power of universality, okay? So there are different ways to look at data that gives you the same level of information. This is, I think, an extremely important concept. Now, funnily, whereas extreme value theory, and this again, the state of the art is never enough, is used a lot, I mean, every day in finance and in hydrology, in the area of geosciences, is almost unnoticed in the IPCC report, which is very funny, especially if you want to use data to inform operators in the finance sector about risk, or insurances about risk, because that's their standard way of doing it since decades. And now in the all IPCC report dedicated to extremes, extreme value theory is mentioned 2 times, saying, oh, it's a mathematical curiosity. You can't really use it. Let's stick to the 95th percentile. It's not true. And we did analysis even with one of my students from Pakistan. We did analysis in one of the worst case scenarios. So sparse data, not so good from southern part of Pakistan, and you get really good description of the statistics of extremes. So this is an easy way to look at extremes, and they have bounds and return times and so on. So anyway, extreme value theory has really, I think, given a big contribution to better understand some properties of the climate. But as I said, I will not delve too much, I will not discuss about this anymore. Now, let's go to a question that, of course, Kira is, can I call you Your Excellence or something like that? Your Majesty, no? Okay. So what is the highest air temperature a human body can sustain without dying, Kira?
Well, I'd say 42 degrees internal body temperature gets us to uncomfortable positions, right?
Okay, this is the internal body temperature. My question is different.
Well, that depends on my technological means that I have at hand.
Assume you're naked.
May I add a word?
Yes?
I would say it's not only a matter of the temperature, it is certainly, but also of humidity.
Okay, let's assume you are a comfortable humidity. Let's say, 30–40% relative humidity. So not in a sort of very high humidity. So that's not, no, I know the heat index matters. So, but let's put the problem aside.
I mean, it also depends on the time of exposure.
Oh, good.
You've been to Finland.
Oh, that's exactly the thing.
There is a sauna.
Okay, so I'm a sauna enthusiast, and I even dived into cold water afterwards. And the thing is, that's the answer. So many people say it's 60 degrees, 55, 60. No, it depends on time, because this is the very old tradition of the northern lands. Any vaguely, say, healthy body can go into the sauna and stay 5 to 10 minutes. 90 years old people do it regularly, and they don't die. Actually, it's considered to be very healthy. Children do it very, very early in their age. So the problem, and this is the 80–90 degrees at very low humidity. So the problem is how long you stay there. So we see that the damage inflicted by an extreme has to do with the time scale, the persistence of the extreme. Look, I like a lot this figure on the bottom right. This is the line with dots, is the measure of the temperature in France during the 2003 heat waves. And the histograms give you the excess mortality. As you see, the excess mortality grows with the time, the length of the heat wave. So you see that the number of deaths go quadratically, approximately, with the length of the heat waves. So at the beginning, the heat wave is not killing anyone, because everyone can sustain 1 day of very hot temperature. But when it's 2, 3 to 5, 10, 15, people start to die. Okay? So that's a very important problem, because your resilience has to do with the time scale, the integrated, if you want, forcing. So it's degrees times days, it's not degrees. That's very important, okay? Of course, there is an absolute threshold. You cannot enter a voodoo oven, you die. But that's an absolute threshold, okay? Now, so the point is, we don't want to look at extremes of hot days or cold days, or not necessarily. This can be important for certain applications, but we want to look at extremes in terms as heat waves and cold spells. So something that is large and persistent. So the way, and keep in mind that this is a general property of the atmosphere, that there is a relationship between spatial and temporal scales of a phenomenon. So if a phenomenon is persistent, it will have also a large spatial structure. So we will see. So automatically, by looking at large persistent events, we will look at large scale events. So this brings the problem, if you like, impacts of systemic risk. So the risk is not going to be just limited in a region, can extend on continental scale or global scale almost. Okay. Now let's look at the 2010. For once, I started to do a work looking at case study instead of my mental masturbations about equations. So an important case study: 2010 heat wave in Russia, centennial event. 1 month of hugely high temperature in Russia, forest fires, catastrophe, literally at many levels. At the same time, there was a connection, dynamical connection that led to floods. I mean, what people would call floods of biblical proportions in northern Pakistan that displaced 20 million people. So these are the numbers we're talking about. And this has there are some really beautiful papers where people study the dynamical connection between these two events. And in a recent paper with a former student of mine who graduated actually in Hamburg, we did a backtracking of water parcels from the region of precipitation, and we did find the connection with the blocking structure that led to the Russian heat wave. So you see the problem of so-called cascading extreme events or correlated extreme events. They come also from the presence of persistent structures in the atmosphere. So you need time to build up mass, okay? That's a problem. Now the framework to look at this is, from my point of view, the best one is so-called large deviation theory. So we consider the mathematical, I mean, this is one of the biggest success story of probability theory and statistical mechanics and so on. But in a nutshell, it's very simple. I have a sequence of identically and independent, for the moment, distributed stochastic variable xi, and I study the statistics of their finite time averages, 1 over n sum of xi. So we say that these variables obey a large deviation principle. So if in the limit of n becoming large, the probability as the exponential function of the form e to the minus n, where n is the finite time, the length of integration, times a function, which is the so-called rate function. This rate function has a minimum, which is 0, on the actual average of xi, and it's larger than 0 elsewhere, saying that if you look at longer and longer averages, guess what? The average will converge to the asymptotic average. And this is an extension of the central limit theorem. There are lots, I mean, this is a very complex story, but this is just the nutshell. So the idea, but keep in mind, keep in mind that if I'm able to estimate I of A, because some of your friends among the angels told you what is I of A, you are able to predict the probability of occurrence of events of any length, n. So you have predictive power in terms of persistence, because you can change n, and intensity, because you can change A. So if you have I of A, you have n informations on extreme events, both in terms of their size and persistence. So this is you see, this is very powerful. Now, and this is the idea. So if I'm able to estimate this rate function from data, and I am pretty happy with my estimate, I have predictive power for events that are longer persistence than what I have ever observed. So I have out of sample predictive power, which is what you want. Otherwise, remember, you can always do an empirical frequentist statistics, but then you have 0 predictive power or anything that you have not yet seen. That's why we do a fit with respect to some family of distributions to have some predictive power. Things, what I said has to do with the case of independent stochastic variables, but can be accommodated for serially dependent stochastic variables, and the things change a bit by adding the so-called integrated correlation times, which is basically a folding time in the case of exponentially decorrelating system. Not exactly, okay? Now, this is the basic of the theory is the following, is that large deviation laws describe typical persistent events in the sense that they are the most likely among the extreme events. So the most likely among the least likely events. Okay, this expansion does not tell you the whole story. It tells you the story that it's dominant for n going to infinity, but it can leave out other events that are not in these statistics that I would call freak events. So these are events that are outside these statistics and can still take place. And you can call them using Cernet language the dragonkins. Some people like this terminology. So what is not inside the large deviation statistics is in some sense a freak event. It's something very strange, but it can still be there, okay? So now, starting point of the study came from, I mean, the work is done with Melinda Galfi, then my student, and now she's postdoc in Uppsala. So we started from a simple model. So we did this in a sort of physicist approach. So starting from a simpler model where we have control and then go to more realistic case rather than shooting in the dark. I mean, this is my way of working, which is sometimes boring. But now the idea is we took a so-called primitive equation model. So this is a model of the Navier-Stokes equation in quasi-hydrostatic approximation in a rotating frame of reference. So this is a system which has it's in a turbulent regime, as you know, maybe 100 positively up of exponents, dimension, Kaplan-Meier dimension of 200. So it's a highly dimensional turbulence case. And then we studied something very simple, the large deviation laws of temperature at the surface. Okay. Oops. Yeah. So this is reported in this paper in Journal of Statistical Mechanics. So what we did is let's go back to the title of this seminar, relationship between spatial and temporal scale. So now you look at this is a model which has cyclones, blockings. You know, if you look at it, you see the phenomenology of the atmosphere in a simplified yet Earth-like way. So look at these two panels here, and they represent, in one case, for a fixed longitude, how the temperature changes with time. Okay, so let's say you take Greenwich, doesn't matter, okay? And in the other panel, that's the left one. In the other panel, you say, okay, for a fixed time, I look how the field changes in longitude. And you see that the two things look qualitatively similar. Of course, if this were a wave, by definition, you would get the same. Of course, the atmosphere is a beautiful mixture of turbulence, waves, and features like cyclones. So, but the message is, you see here, there is clearly some relationship between spatial and temporal scales. So now, to make a long story short, because I want to focus more on the last part of the result, is that in the theory, for large deviations, you can do I'm talking about averages of identically distributed stochastic variables. But if I have a system like this, which has symmetric boundary conditions, has no orography, so if I take a longitude, along the longitudinal circle, all variables, all temperature at all grid points are identically distributed, but of course they have a correlation. Similarly, if I take one location, the values of the temperature at different times similarly are identically distributed by stationarity. So you have discrete symmetry versus stationarity. The nice thing is that if you look at averages in time or you look at averages in space, you get a closely related large deviation law. So there is the beautiful thing is that once you look at the symmetry between spatial and temporal turbulence emerges when you look at longer persistent events. So that's the message. So in some sense, looking locally in time, but on a larger spatial scales is statistically equivalent to looking locally in space, but over longer averaging time. Okay, so that's what the theory somehow dictates. And the thing is, in the next slide, so this is, okay, the bottom and so the top is the temporal rate function obtained by averaging over time, and the bottom is the spatial rate function computed averaging over space at fixed times. So this is the first result. We are able to see a space-time symmetry, okay? And in the case of space, you have an average, you have an integrated correlation time. In the case of space, you have an integrated space, and the ratio is, guess what, a velocity. And this velocity is of the order of magnitude of the velocity of winds, order of 1 to 10 meters per second. So you really see the propagation of anomalies in this way. Now, and I come to the end here of the first part, is you can do averages in space, you can do averages in time, or you can do, instead of binge drinking or binge eating, you can do averages in space and in time. So what happens is that in a sort of a nice, I'm talking to people based in the centers of, German idealism and romanticism, and so if you do averages in space and then averages in time, or averages in space and then average in time and then average in space, you're basically talking to the angels because you're going through this class of universality I have just described. So everything works fine. So you can construct the same rate function as averages in space and in time. So you have a sort of, you combine the two, but you are already in a class of universality, so nothing happens. Okay, but you can make things a bit more complex. So if you do an averages, you average in space, but not up to the asymptotic limit. So you average on scales of a few thousand kilometers. You discover that now the rate function is less steep. So compare in the center panel here, the black line, which is the asymptotic case, to the green one, which is asymptotic, but where you have fixed as spatial scales, say a few thousand kilometers. So you see that the red line is flatter than the black line, clearly, much so. So if a rate function is flatter, this means that the probability of occurrence of large events is higher, because remember, the probability goes to n to the minus n times this rate function. So if it increases faster, the probability decreases faster. So this tells you that if I select as spatial scales, this I'm talking about the mid-latitudes, scales of few thousand kilometers, it's more likely to have large temperature fluctuations. What are those? Those are blocking events. So we have found that there is a special scale which is inside the dynamics of the atmosphere where these events, persistent large events, become easier. And this scale is the scale of blocking events. So that was encouraging. I like that result. Things work well in terms of return time, but this is otherwise, the paper would, the whole idea wouldn't fly. So we get a sense of universality and we are able to relate spatial and temporal fluctuations in a very hopefully sort of promising way. But this is, in my split personality, this is the work where you have this nice model, you have symmetric boundary conditions, you have all these symmetry properties. So now let's tear down this. And let's follow the long journey of climate models. So up to now, we were in the extreme left. So I've been using a model which is, definitely a complex model with, well-developed turbulence, but it's all symmetric and it's without colors. What attracted me to geosciences from being a physicist was that suddenly things were not just grayish, but they started to have colors. And this is the beauty of geoscience. And so let's put color in this, in the sense that we went very much out of the comfort zone and we look at the outputs of one of the big, of course, if you guys, sorry, I'm talking in German. So by definition, by very definition, the best immortally unbeatable climate model is, of course, produced at the Max Planck Institute, of course, Savas Sandir. Of course, this is one of the, most important, most used and most respected state-of-the-art climate models used for CMIP 6. So this is a true climate model with 10 to the 8th order degrees of freedom, which runs only with a very heavy HPC technology. And this is used for climate projection now. So we took this model and we repeated the same story. So our goal was to understand the Russian heat wave and to understand something that is much less popular for obvious reasons of Euro or Western world centrism, That is, in the same year, in January, there was a huge so-called Zud event. So this is a very intense, a very, very persistent cold spells that touch the central part of Eurasia, and in particular have historically impacted the nomadic populations, and in particular they are very important for Mongolia, not only economically but historically. Keep in mind that if you double check the records of the Chinese Empire, you discover that all the movements of nomadic populations, from Attila to the Tamerlan or wherever, come following few years of consecutive Zuds in Mongolia. Okay, so these are drivers of major migrations because they destroy, even today, 50% of cattle or so. Some regions, basically, even nowadays, you have people that lose everything, they have to migrate. So think about how it was 1,000 years ago. So these two events were centennial events. And our goal was to understand those. So what we did is, okay, can we use all this machinery of large deviation theory to study this? So now, for those of you who are a bit older experience in climate, so before the tipping points was the keyword, and after the hockey stick, so before Breaking Bad and after Sex and the City, we had lost as major TV serial, that is the climatic hot spots. So you couldn't even, in your dreams, think about climate in the notice without thinking about the climatic hot spots, which comes from a very good and very influential publication by Filippo Giorgi from ICTP, who identified some regions in the globe that were called climatic hotspots where climate change was particularly dangerous. Entire policies of adaptations are based on that. So we took regions which are closely mirroring those, and we tried to say, okay, can we establish large deviation laws? So in other terms, do a climatology of heat waves and cold spells for winter and summer for these regions, and for some locales inside these regions. So grid point versus spatial averages. So the answer is yes, a convincing yes. This was done on two cases. So on climate, on the 1,000 years control run of the Max Planck model, and a 140 years 4 times CO2 control run also of the same model. So the message is you get a clear climatology that works really well of cold spells and heat waves in all land regions, whereas in the ocean, as well known, where there is long-term memory, you don't get this convergence. Otherwise, you see all the characteristics of continentality. So the rate function is much broader in, guess what, in Central Eurasia than on the Mediterranean, which has notoriously small fluctuations of temperature. Ask Goethe why he used to go there. It was not just the average temperature, it was the stability of climate. This is very important. So you get, this is the summer rate functions for pre-industrial climate. And this is the winter rate function, which are much flatter because in winter, the weather variability is much larger. But this, remember, this allows me to infer the probability of occurrence of long and large heat waves and cold spells.
Valerio, sorry, could you go back and say what's the black and what's the red? The red are the different.
Yeah, these are the. You just look at the let's say the black here. Okay, in the sense that these are the estimates obtained for longer averaging times of the rate function. So you see in some cases convergence, some says not. This is another story. Here I'm interested in the black. So as an example here, you see that in Northwest America, in winter, this rate function is very, very, very broad and similar in Northwest Asia, Northeast Asia. This is where you get these cold spells, monster cold spells in winter. Whereas, of course, this rate function is much less, much steeper in the Mediterranean because it's very hard to get large temperature deviation. So it gives you a meaning to the concept of continentality on longer time scales. Okay, so this is the idea. Now, if you look at 4 times CO2 simulations, the message is the summer heat waves become much more dangerous, not only because the average temperature shifts, but because the rate function everywhere become flatter. So it's much easier to get large fluctuation from the average. And the main reason, I believe, is the drying of the soil. Okay, that's the message. In winter, you see, compare this with this. So the rate function become much, much steeper. That is, the winter temperature fluctuation will become much, much smaller. So not only you're gonna get warmer temperatures, but the large negative fluctuations of temperature will become much rarer. Okay? So that is another sort of information of climate change. Of course, that's now something I will, okay, I will skip this for the moment. And now we go to the end, getting the events right. So now, as I said, can we understand, okay, this is a statistics, it's a climatology, fine. Can we learn something about the dynamics? And the answer is yes. By focusing on large deviations, we are able to decode some special feature of the natural variability of climate. And in particular, show you that events like the Russian heat wave are inside the climate variability. So their probability of occurrence changes because of climate change, but their dynamics is something very deep because we reconstruct everything just with a model run that doesn't know anything about climate change. Okay? So it is something inside the variability. Climate change changes the probability of occurrence. So it's a different story. So this was the Russian heat wave, as I showed you before. So now these are the temperature fluctuation, the temperature anomaly in August 2010, observation and reanalysis, and the lines gives you the isoline of pressure of the 500 hectopascal geopotential height, so the large-scale atmospheric pattern. Look at the size of the domain, it's important. So now I say, I have this 1,000 years on run, I choose the events where in the point, the green dot, which is basically the city of Moscow, I have temperature anomalies of 4.5 degrees or larger, lasting at least 30 days. So something that matches the observations. And this is the average of the fields I get. And as you see, it looks at least qualitatively very similar to what was observed in that month. And if I change the intensity of the anomalies or the length of the anomaly, things stay the same. This is very important. So here you are looking at a very special region of the phase space, and you are finding a very special way to get there. Okay. So now you repeat the same for the Mongolian Zud. Look at the size of the anomaly. This is the entire Eurasia. So this is a 10,000 kilometers event. Okay, this is enormous. And again, you get that by looking only at the events where you look at the large anomaly in a place which is next to the city of Omsk, by the way, very center of Siberia, you do the same operation and you find temperature pattern that is very similar to the observed one, and special pattern of a temperature and geopotential height that is similar to the observed one. So that means what you observed looks similar to what the model gives you. And I can tell you that if you look at the individual realization, they all look very similar. So strange, you say, oh, come on, I observed one event. Why should it look at all like something the model tells me? And this goes in the direction of what I mentioned before. The large deviation theory tells you, if you observe such a large event, you most likely will observe something that obeys large deviation statistics, because the other events are exponentially less likely among the class of the unlikely ones. Okay, so this is the idea. Now, in some sense, these events are not exceptional. They are large, but they are inside the statistic. The good news is that these are part of, if we look at the system in the right way, so according to these statistics, these events become typical. So there is a typicality in extremes that we are able to recognize. Now, what about, at the beginning, I said about precipitation in South Asia. And if you repeat this, surprisingly, you get the right, I mean, something that is a very close match to the pattern of precipitation in South, Southeast, and East Asia. That means you're really getting the dynamics right. Because to get the precipitations right, 5,000 kilometers away, it's very non-trivial. You cannot just be lucky, okay? And then another story is that using this approach, you are able to predict the return times of yet unobserved event. I will not go into that. So you have predictive power on events that you have not observed. Final case study, still unpublished, 2018, cold spell in Calgary. It's centered on the city of Calgary in Canada. So this is February 2019. And this is an anomaly of about minus 10 degrees lasting a month. So a monster that took half of, you see, North America. So this is the global feature. So it's, of course, it's a large-scale event. And now you shouldn't be surprised by it. And this is what the model, the bottom is what the model tells you. And you see that there is a dipole, cold in the west, warm in the east. Okay, you say, okay, North America, come on. What else could you accommodate there? One could say, well, cold everywhere. But the model finds it the right pattern, not by chance, because this is the global pattern. And the model finds also positive anomaly in Northern Siberia and in West Europe. And warm anomalies in the east and south central part of America. So you see that really you're getting something fundamentally right about the dynamics. And same with precipitation. How have people interpreted these sort of events? There is a growing body of literature where people study these persistent extremes, in particular some nice publications by Kaika and Uba and others. So let's say a group of Round, Pick, Potsdam, and they use the other collaborating institutions. So the concept they use is the concept of standing Rossby waves. So that's a super classic of Rossby waves like harmonic oscillator for physicists. So is something of enormous importance, of course, in meteorology. So you say, okay, well, I have these persistent events if I have a standing wave that persists. But to me, this is almost a circular argument. So what I'm telling you is that I think there is a different way to look at these features that relies on looking at the statistical mechanics of it, rather than at the dynamics around the event. And I think our method is in some sense more powerful, or at least has different advantages and different disadvantages. Okay, I'm done. Thank you very much.